Okay, so yesterday I gave you kind of a general overview of fixed order and what the ingredients are in terms of scattering amplitudes. And today I want to go through more kind of a little more one loop details. There's two aspects to it. There's evaluating the Feynman diagrams and evaluating the loop integrals. And I'm only going to sort of touch on the kind of evaluating the Feynman diagrams in a on-shell approach, which is why I wore this t-shirt. So we're going to use methods that sort of use put internal legs on shell and allow you to simplify things, also make use of connections to other theories. Now, I would never say anything bad about any other methods, but so if you remember from last time, we had these properties of tree amplitudes, which I didn't really go through because I don't really want to develop all of the spinner techniques here, but I just told you about them. Maybe I should just list, there are a bunch of references if you want to know more about spinnerology, other amplitudes techniques, also color decomposition. I'm not really talking about too much. So I wrote a old TASI lectures, but it still has kind of the basics in it. There was a little review, mini review of the loop stuff that I wrote with my collaborators in 2007. There was another review of one loop QCD techniques by Ellis, Kunst, Melnikoff, and Zandarigi. There's a book by Elvong and Huang. And just recently, there's one by Simon Badger in Torino, Hen Plefka and Zoya, also I think in Torino. So there you can get 291 pages of this stuff. Anyway, so there's a lot of reviews. I don't have of more details of on-shell methods than I have time to go through here. But let's just look at this example. Remember, we said that we only need two different one-loop amplitudes to do gluon-gluon scattering. And one of them was this one. The other one is this configuration. So we can start by trying to take a discontinuity and ask what piece of this amplitude can we see if we consider the imaginary cut in the S channel, where S is S12. So when you draw such a cut, you're requiring legs to go on shell in the middle, and at one loop, you want to look at least two legs going on shell. And this is called standard unitarity. You can also do generalized unitarity, where you put additional legs on shell on either side, but we're not going to get to that. You can read some of these for more on that. And then the next thing you need to do is to decide what velocities are crossing the cut. And remember, we have this all outgoing convention, which means we talk about the helicity as if that particle were outgoing. But whenever we cross the cut, an outgoing particle on one side is carrying a momentum that's incoming from the point of view of the other side. So to be consistent with that labeling, where you have to switch the direction of the momentum while the angular momentum stays the same, you have to flip the helicity when you go across the cut. So you need to always do that. But now look at this side over here. We have 2 plus helicities. If we put 2 plus, we would get 0. Or if we put one of them minus, we would get 0. So we have to have 2 negative helicities here. And then on this side, we have 2 positive helicities. And then we can use the, so if we call these 2 loop momenta L1 and L2, then this formula is, I didn't tell you in much detail what these guys are, but we're not going to really evaluate this anyway. So, this is called the Park-Taylor formula. And it has the 2 negative helicities appearing in a spinner bracket in the numerator to 4 powers. And then you just write down the string of spinners around the outside. And that's one factor in this cut. And then over on this side, we can write down the 2 negative helicities and then the chain of spinners. So I'm just using from memory the Park-Taylor amplitude, and I'm relabeling it to correspond to these cut momenta. So the point is, you learn a lot about a one-loop amplitude by just writing down these products of spinners. Now you have to do a little rearrangement on this and use some spinner algebra. But when you do, you find that you get S12, S23 times the tree amplitude times 1 over L1 minus K1 squared, 1 over L2 minus K3 squared. So you do a little bit of algebra and you get this form. And then you recognize this form as being the cut of a scalar box integral. So this, when I draw this with straight lines like this is what we call the zero mass 4-point or box integral with nothing in the numerator. And in dimensional regularization, it's d4 minus 2 epsilon of L times the product of 4 scalar propagators. I guess I'm calling this, I'll call it P here. So there's a P squared here, and my momenta are outgoing, so there's a P minus K1 here, and so on. So the cut of this integral, where I cut these 2 lines, it just replaces these guys with delta functions. Well, I was calling it L1 squared over there. And that turns this into an integral over the 2-body phase space for this L1 minus L1 L2. And then it essentially removes these propagators. It replaces them by delta functions, which reduce the loop momentum to a phase space integral. And it only leaves behind these 2 propagators here, which have P plus K4 and P minus K1. So if you do this spinner algebra and you come up with this formula, you understand that these propagators here represent the propagators of a cut box integral. And therefore, this answer for this helicity amplitude, you've already learned that it is equal to, maybe there's a, I'll check this sign in the overall thing in a second, but, and by the way, this tree is just one. And then we just write down the full box integral, removing the cuts. We could be missing some stuff, so we could be missing stuff with no S-channel cuts. By the way, notice that there are no matter contributions. That is, we have fermion helicity conservation tells us that if we were to put a fermion loop in and we cut it, then we would see two fermions, but they would have to have opposite helicity here in the all outgoing convention. And that's not allowed because these amplitudes vanish. By the way, the scalar amplitudes, even though scalars don't have helicity, you can kind of form them into complex pairs. And the anti-complex one is sort of like negative helicity, and it obeys this rule too. So you couldn't have scalars in the loop either. Why do I mention scalars in the loop? Because in n equals 4 super Yang-Mills, you're right, remember, there are fermions in the loop and there are also scalars in the loop. Since they don't appear here, it's very similar to the argument we had at tree level, where we said the tree level gluon amplitudes were the same as they are in n equals 4 super Yang-Mills. Well, this piece of this loop amplitude is also the same as in n equals 4 super Yang-Mills. And I can't go through it now, but the fact that this comes out to be just a scalar box is something you can prove very generally for n equals 4 scalar one loop amplitudes. You get only boxes. So the other things that you could have in this process besides boxes are triangles and bubbles, where you have canceled propagators of some of the boxes. And so at this point, we don't know, we know that we don't have any triangles like this. We would call this an S-channel triangle. We know it because we did this cut, or somebody did this cut, and you can detect this triangle. So those are not there. But we might still have a triangle oriented this direction, which I call a T-channel triangle. And the reason is that this propagator has been canceled. And these cut conditions require both of these propagators to be open. So we could have triangles like this, or we could have a bubble in this direction. So to ascertain whether those are there, you have to go do the cut in the other channel. So you need to go draw something like this. And in this case, because this is minus and this is plus, we're allowed to have a plus here and a minus here and a plus here and a minus here. Or we could flip them around. And in this case, I drew them for the case of fermion, because in this case, the fermion is allowed, and so is the gluon. And you could also put scalars here too. So if you actually do this for the case of a fermion plus a scalar, this turns out to be an n equals 1 SUSY matter multiplet. And I'm not going to go through the algebra, but you find that you get something that is proportional to this scalar bubble integral. So this is an integral dp looks something like this. So here's P, and here's we emitted K1 and K4 to get P minus K1 minus K4 over here. And this integral turns out to be something like 1 over epsilon plus 2. It only depends on this T-channel guy, S23. It basically looks like this. And so you find then that for the minus minus plus plus configuration, which I'm not going to keep writing, the NF term plus the NS term is equal to A4 tree. There's some standard normalization stuff. So, and then there's a 1 over epsilon times minus S23 to the minus epsilon plus 2, which comes from this scalar bubble. If you do it for the scalar alone, you get instead a 1/3 times this for the singular part. And because in this case you get some loop moment in the numerator of the bubble, you get a slightly different thing here. And the fermion one then must be the difference of these. So you get these terms. Now, these bubbles, they're not allowed in n equals 4 super Yang-Mills. And so the A4 gluon from the T channel, it's actually, this bubble isn't there in n equals 4 super Yang-Mills, but the n equals 4 super Yang-Mills has a gluon in it, and then it has 4 fermions, and then it has 3 complex scalars. Anyway, using that fact, you can rewrite this as minus 4 times the NF term, minus 3 times the NS term, and that turns out to be same overall factors. So does anybody remember this number minus 11/3? This shows up in the one loop beta function of QCD. It's the beta function for Yang-Mills theory. Has an 11/3 in it. So the beta function for QCD is actually something well, depends on your conventions, but it's 11/3 NC minus 2/3 NF. These gluons are in the adjoint representation, and when you go through the color algebra, this graph is really supposed to get an extra NC, which corresponds to this NC. And this, here's the NF term, and you see it has a 2/3 with the opposite sign. And you can go check, if you don't believe it, that the -4 times this one, -3 times the scalar one gives you this one. So you can get the beta function of QCD out this way. Now it's a little bit of a cheat because this is an on-shell amplitude and it has an ultraviolet divergence in it, but it also has some infrared divergences in it, which have exactly the same form at one loop. It's kind of bizarre, but you would get the wrong sign for the beta function if you forgot about that. And it's actually happened before. So there's, I mean, some people might have gotten the wrong sign for the beta function back in the 70s, but some people also maybe got the wrong sign from forgetting about the IR divergences here too later. There's also this finite piece, and that one turns out to be related to something called the cusp anomalous dimension at 2 loops. You have to be, in this case, you have to be in the right scheme. And this supersymmetric scheme is not the scheme people normally use. And when you shift to a more conventional scheme, there's an extra little bit here where delta R is 0 in what's called dr bar, which is supersymmetric. But it's 1 in conventional dim reg. Well, actually a Tuft-Veltman scheme. But anyway, the 1 here gives a 67/9. And this number actually shows up in the cusp anomalous dimension. So I didn't show you all the details, but it's relatively simple to do simple loop calculations like this. And you can do much more and make it more automated. And there are other closely related techniques, and they've been used to produce a large number of sort of automated one-loop programs. So let's see, was there anything else I wanted to say about that? I think that was about it, unless there are any questions. Otherwise, I will move on to just say a little bit about, start talking about loop integrals. For example, we need to evaluate this integral. But were there any questions? And I apologize for being somewhat schematic, but I hope you get the flavor of the idea that by putting these legs on shell in intermediate, you can reconstruct most of the answer. There was one thing I didn't point out. You might know that the strategy of getting a full answer from the imaginary part sometimes goes under the name of dispersion relations. And there can be needs to do subtractions, and the dispersion relation might not be completely enough information. And the same thing is sort of true here. There are certain rational terms that don't have any cuts in 4 dimensions. However, they generally have cuts in d dimensions. And so if you use unitarity, but don't take it more seriously in d dimensions where you can't use these helicities as well, you can also get out the rational terms in the complete answer. And the other reason for mentioning this is that besides this being the basis of many sort of NLO or one-loop programs, so we had a program called Black Hat, and then there's also Rocket, Samurai. These are all from over 10 years ago, I think. Go Sam. There's one by N-Gluon by Simon Badger and collaborators. Open Loops is some of them are based on another closely related method called OPP reduction. And there's also a MAD loops, which became part of AMC at NLO. So this is all at one loop, all these different programs. And then the frontier is to apply these same techniques at two loops. And there have been various people working on that, including Fernando Febres Cordero, Harold Ida, Ben Page, Samuel Obroy, a number of other groups. And they have a two-loop package called Caravelle. But the two-loop story is even more intricate than what I hinted at for the one-loop case. Okay, so if there's no other questions, let's start talking more about integrals. So we'll just start at one loop. And we start with some integral of an n-gon. So we have an integral like this, and you probably all know that you can treat this integral and change it into a parametric one. So there's a Schwinger parametrization where we write 1 over pi squared as the integral dti e to the minus ti pi squared. If we replace all of these propagators with this, we'll get a term that goes like e to the minus the sum of the ti times the pi squared, where this is p1 squared, p2 squared, p3 squared. And then there's an integral over d4 minus 2 epsilon p. So this is a Gaussian integral. So we just shift the, we write it as a Gaussian integral in p, quadratic in p up here, and we shift the momentum by something proportional to the ti's and the external momenta until it becomes of the form some shifted p hat squared, which has the coefficient sum of the ti's, plus something that's left over. And after you do that shift and do the Gaussian integral, then you rewrite the Schwinger parametrization. You write the ti's as t times ai, where the sum of the ai's is equal to 1. And these become the Feynman parameters. Whereas these were the Schwinger parameters. And then you get, if you write this curly I as something like minus 1 to the n I over 4 pi to the 2 minus epsilon times a straight I, then, and And we put a 1 here to remind ourselves that we just have a 1 in the numerator. Then this Schwinger parameterization is gamma of n minus 2 plus epsilon times integral 0 to 1 of the AIs with this constraint that they sum to 1. And then this Schwinger parameter polynomial is a sum over I and j of some quadratic monomial raised to the n minus 2 plus epsilon, where this matrix Sij is 1/2 of mi squared plus mj squared minus 1/2 of ki plus ki plus 1 up to kj minus 1 squared. So that's an exercise for you to do if you want to work out this formula for the Feynman parametric form. And these mi's are the internal masses. So I guess probably 1, 2, 3. So this might be M3 internal masses. And then there's also external masses here, but those are represented in terms of these ki squared. Notice that if n is bigger than, this is where the UV poles sit. In the overall, they correspond to shrinking all the propagators to 0 at the same rate. And they come from doing an integral over the common parameter t, which has already been done here. And so they sit out front in this gamma function prefactor. But they're only there for n equals 2. And in the massless case, if all the internal lines are massless, then you would not get any tadpoles, but otherwise you would get some there too. N equals 1, or so for n equals 3 and bigger, everything's ultraviolet convergent, but when you have a lot of external lines that are massless and internal lines that are massless, you get infrared divergences, and those come from boundaries of the region of the parameter space. Okay, if we don't turn off the regulation and look at this box example, well, let's do that now. Let's do that example so we can see where the IR divergences come from. Any questions while I'm erasing? So this I40M has these legs here all massless. And if we plug into this general formula over there, we have to work, we plug in n equals 4, so we get gamma 2 epsilon, and then we have Then we need to work out what this matrix S is. And first of all, it's all massless. That means no masses on the inside. So all the MIs are 0. And these guys run from I to j minus 1. So if j is equal to I, you don't get this term, and you only get the mass terms. So we have only zeros on the diagonal. And when j is equal to I plus 1, then we get ki squared. But that's massless too. So on the off diagonal guys, we also get 0. So the only non-zero guys that we get are when j is I plus 2. So if you have 1, 3, you end up getting the minus a half times S1, 2. And here you get, for the A24 term, you get minus a half S23. So we just, and then the half gets canceled by the sum over I and j reversed terms. So that's the box integral in parametric form. And in this case, there's a nice change of variables that helps you separate things out. The problem is that when A1 and, or let's see, you can make, you can kill off both of these terms in various regions, and that they will be exposed when we make this change of variables. So notice that the sum of the AIs, when I add these two middle guys, I get 1 minus y, because z plus 1 minus z is 1. When I add these two guys, I get y, because 1 minus x plus x is equal to 1. So then I get y plus 1 minus y, which is 1, which I had to get for it to be a valid parameterization. And then there's a Jacobian, which involves taking the derivatives of these old variables, say a1, a2, and a3, because a4 was limited by the delta function, and x, y, z. And if you work out the partial derivatives, you get some 3 by 3 matrix. And when you take the determinant of it, you get a y, 1 minus y. But the clever thing about this transformation is that this A1 has a y, and the A3 has a 1 minus y. And the A2 has a 1 minus y, and the A4 has a y. So there's a y and a 1 minus y that come out of each of these. And so you can factor them out. And so the integral I'll just put it on a new board. So the nice thing is that all the y dependence factors out. There's that y1 minus y in the Jacobian, and then we could factor a y1 minus y out of the term raised to the 2 plus epsilon. Oops. So the y integral is given by what's called the beta function. You just get, here's the overall gamma 2 plus epsilon. And then you get a gamma of this exponent plus 1 squared, because it appears twice. And that exponent plus 1 is minus epsilon. And then in the denominator, you get gamma minus 2 epsilon. And then you have just these integrals. And I can also factor out a minus s to the minus epsilon from here. And then we get 1 minus x, 1 minus z plus chi xz, the minus 2 minus epsilon, where chi is t over s, or s23 over s12. So this y integral had a divergence when epsilon is equal to 0 at the endpoint y equals 0, because it goes like y to the minus 1. Has logarithmic divergence there. Has another one at y equal to 1, but it's kind of the sum of the two, not a product. So you expect a 1 over epsilon. You know, whenever you have a integral dx over x to the 1 plus epsilon, you get a 1 over epsilon. So you get a 1 over epsilon from there. So this is minus, there's a 1 over 2 minus 1 over 2 epsilon as epsilon goes to 0 in this gamma function. And then there's minus 1 over epsilon quantity squared here. So I think you get a 2 over epsilon. So you get you get a 1 over epsilon from here. But then you also have endpoint divergences here. So when, let's see, when x goes to 0, then this sorry. First, we're going to do the integral over z. This integral over z ends up being chi x to the minus 1 minus epsilon minus 1 minus x to the minus 1 minus epsilon over 1 plus, that's an elementary integral, which these days means Mathematica can do it. Actually, Mathematica can probably do all this, but okay. Okay, so now you see, as x goes to 0, term turns off, doesn't matter, and you have an x to the minus 1 minus epsilon. So you're going to get a 1 over epsilon from x equals 0, and you're also going to get a divergence at x equals 1 that comes from this term. So you could actually do this whole integral exactly in epsilon, but for more complicated integrals, nobody ever wants that. They only want an expansion in epsilon through epsilon to the 0. Or if you wanted to do this at NNLO, then you would expand it 2 orders further, because in the squared one loop amplitude, remember a minus 1 over epsilon squared on one side could hit an epsilon squared on the other side. but you never want to know it exactly in epsilon, so you don't need to do it exactly. What you need to do is you need to find a way to simplify the answer so that the subtracted result is finite. So at x equals 0, to cure the x equals 0 divergence, so I should say for the x equals 0, you subtract and add the x goes to 0 behavior of this, which is chi x to the minus 1 minus epsilon, 1 plus epsilon. And then to fix the x equals 1 behavior, you do the same thing with, see, this is just the x goes to 0 limit of this. I just dropped this at that point. And in the x equals 1, I plug in x equals 1 and I get a chi in the denominator. So I have to do one reason I'm kind of going through the gory details here is because this is analogous to the kind of thing you do when you build these subtraction terms for real radiation. It's an overly simplified version of it, but you subtract off something that you know how to integrate that's divergent, and where the difference then becomes finite. So when we add this back by, we're going to subtract it from these and treat that term together, and similarly with this one. But in the one where it's alone, we just get to use this formula. Maybe it's minus sign, I forget. Anyway, we get to use this formula to work it out. So in the non-subtracted terms, so from those terms, we get a gamma 1 plus epsilon, gamma squared of 1 minus epsilon, gamma 1 minus 2 epsilon. That comes from shifting these arguments to expose the minus 2 over epsilon inside those singular gamma functions. I think I forgot a 2 over here. S is S12. And then there's a minus 1 over epsilon times a chi to the minus 1 minus epsilon, which comes from integrating this term. And there's a minus 1 over epsilon times a chi to the minus 1 from integrating the second term. So this is the just from the subtraction terms when added back. And that ends up being something like 2 r gamma over epsilon, or r gamma over st times 2 over epsilon squared minus S12 to the minus epsilon plus minus S23 to the minus epsilon. And this R gamma is just some combination of gamma functions you often get at one loop. But it's basically 1 minus maybe a half of zeta 2 epsilon squared plus some other stuff. Oh, and there's a e to the minus Euler gamma. And then there's the subtracted integrand, where you just need to series expand it in epsilon. And you find that the epsilon of the 0 term vanishes, but there's an epsilon to the 1 term, which you need because there's an overall minus 2 over epsilon. So you need that even if you want to get the order epsilon to the 0. And then you get log of something like chi x over 1 minus x over 1 minus 1 plus chi x. And if you do this integral, you get some epsilon and then a half of log squared chi plus pi squared. And if you put everything together, those two pieces together, you get that I for 0m is equal to minus r gamma over S12, S23 minus 2 over epsilon squared and then recall that A for 1, 1 minus 2 minus 3 plus 4 plus was essentially this box integral. It's so we talked about the bubbles earlier, that they have only 1 over epsilon poles. But this box integral, the S12, S23, which is its coefficient here, cancels. And we get a statement that the infrared divergences are proportional to the tree amplitude, which is a standard thing. And also, there are 1 over epsilon squared terms that come from the overlap of the soft and collinear virtual divergences. If you expand this out, you see there's a 1 over epsilon, which now depends on the kinematics. It has a logarithm of S12 in it. And so this piece of it kind of knows that the divergence is coming from a soft region in the vicinity of these legs S12. And this too actually comes because S34 is equal to S12. And so that logarithm of S12 could also be a logarithm of S34. And the fact that you get both of them, you end up getting this too. If you did a more complicated process, like with 5 gluons, where you don't have this identity of between the kinematics over here and the kinematics over here, you wouldn't see this too. You would see instead a sum over minus 1 over epsilon squareds with a 1 times SI I plus 1 to the minus epsilon. Now this is the soft collinear leading color piece. And there should really be an overall factor of NC, which I've been loose with. But anyway, you can understand a lot of these factors. If you want to do full color, you're going to get these T operators that Emanuela presented yesterday appearing in the formulas for the divergences, as first written in that notation by Catani. Okay, any questions about that? you can go through similar techniques and work out all the massless boxes, but doing it all directly is not really the best way to do it, especially when you go to two loops. So when we get to two loops, we're going to do things differently using integration by parts methods and differential equations. I do want to mention, though, that there's a relation between higher point integrals and boxes. So in some sense, boxes are all you need at one loop. So there's a statement that pentagons and hexagons are not really independent of the boxes. And I'm going to just give you a heuristic reason why that should be true. And it's based on sort of cutting lines. So we're going to write a pentagon, for example, and then we're going to imagine cutting these lines here. So here's P1. So we're going to impose P1, Pi squared equals 0. I equals 1, 2, 3, 4, 5. Now remember that P2 is not really independent of P1. It's P1 minus K1. That is, there's a loop momentum here, but we think of the external momenta as fixed. And so the cut conditions, we're doing it holding the external momenta fixed and just doing it as a function of this loop momentum P. So P1 is equal to P, P2 is P minus K1, P3 is P minus K1 minus K2. But the degrees of freedom we have to solve these 5 equations are the 4 components of P. So we only have 4 components to P, and we have 5 quadratic equations for them. And so generically, you can't solve them. If the external momenta are in a sort of generic configuration, you can't solve all these equations simultaneously. So what does that mean? It means that the rational function must somehow decompose into things that only have subsets where at most 4 of the momenta go to 0 at a time. So as a rational function of the momenta, this can't really have 5 separate singularities. So it must be possible to partial fraction it out and to write it as a sum of terms which only have 4 of the 5 p squareds. Here's one term. There could be another term. And I didn't say what these coefficients are yet. So another term would be, and in general there should be 5 such terms where you kind of delete one of the 5 propagators in each term. And this is just because you can't send all of these guys to 0 at the same time. So the result is that you get an equation like this, that the scalar integral for the pentagon in 4 minus 2 epsilon can be written as a sum where you cancel the ith propagator. And there are 5 of them, so there are 5 terms. And then there's a correction because this argument is not quite valid when you dimensionally regulate, because there is a 5th component of the loop momentum in the sort of extra dimensions of dimensional regularization. And that gives you some mostly harmless extra term, which is the pentagon again, but in a shifted dimension. And then these coefficients, they turn out to be related to, you take this S matrix of the kinematics and you invert it. And then you take the ij and you do this sum. And C0 is this, so that gives you the coefficients of these boxes here. And then C0 is the sum of all of these, which is also a kind of related to a determinant. So this extra correction term is pretty harmless because this is, at least at next leading order, because this is finite as epsilon goes to 0. You can check that there are no UV divergences, even though it's in higher dimensions. It has a lot of propagators. And the fact that it's in higher dimensions regulates all the infrared divergences. So you can completely neglect this guy at when you only need things to order epsilon to the 0. And then there are similar relations for hexagons, but there's in that case there's no epsilon correction. So these relations were worked out by Van Nerven and Vermaaseren long ago in like 1984. And then we upgraded them to dim reg in somewhere around here. So sort of with those results, then you don't need, every amplitude is a linear combination of boxes at one loop up to these higher order corrections and triangles and bubbles. And then the task of unitarity is to determine the coefficients of all of those. There's also the issue of what about if you have tensors in the numerator, and if you have tensor integrals that you need to reduce, you need to think about that a little bit. And again, some of this at one loop is very old technology. I'm kind of mentioning it because it works. We'll come back to it at 2 loops slightly differently. So a tensor integral we might write like by putting some tensors in the loop momenta in the numerator. So here's the same endpoint integral, but now I put a bunch of tensors in the numerator. So if the p mu's are contracted with external momenta, then we're in luck, at least in the first stage. Because if we have a loop momentum contracted with an external momenta, we can write that as a difference of propagators plus constants independent of the loop momenta. So if we take this propagator, where I've subtracted off all the ones through I minus 1, and then I subtract from it the ones where I do all the way through I, that will cancel all of the dot products. We'll cancel the p squared and all the dot products until I hit I, and then I'll get this guy. And then you just have to correct for the terms that are independent of p with something like this. So these are constants. So this gives you if you only had one power of 2p dot ki in the numerator, this would give you an endpoint integral without that power times this stuff. You could pull it out of the integral. And this will give you various n minus 1 point integrals with different terms, propagators canceled off. Something like in, I minus 1 minus in. So this tensor reduction is easy, but you're not always that lucky. For example, you might have a polarization vector for a gluon. Or you might have two powers of this. Then you can use this identity once, but after you use it for the first guy, you will have lost some of the propagators, and then it's no longer possible to use it the second time. So the solution for that was called Passarino-Veltman reduction. And it says that if you have something with one tensor, you just use Lorentz invariance, and you say, the only things I can build this out of are external momenta. So I just write down the independent external momenta. If n is not too big, then using linear momentum conservation, the first n minus 1 of these momenta are independent. And so I can write an equation that relates this thing for a general index, Lorentz index mu, to a bunch of other quantities which are scalars multiplied by the external momenta. Or if I have two of these indices, then I could write down a similar thing using both pairs of momenta. However, there's also a now you don't, when you're using unitarity, you don't actually have to go through the details of this reduction. You just have to do a Gedanken reduction that says it's possible to implement this procedure to reduce things essentially down to scalar boxes, scalar triangles, and scalar tensor bubbles. And then you have to figure out how to extract the coefficients. But if you were handed an individual diagram and you wanted to reduce the tensors in the numerator, you would relate them to these quantities here. And then the next step would be to start then you have to figure out what these things are. And so then you contract these with these equations with external momenta. Okay? And then you start solving for these coefficients. I'm not going to go through the whole procedure. I'm just going to mention that when we solve for these coefficients, we have a bunch of contractions of ki's with kj's. And we're going to invert a matrix of those in order to solve these equations. So we have to invert some matrices that involve this. It's similar to this Sij matrix, but not quite the same. It's the matrix of two ki dot kj's. And that leads to denominators which involve the n minus 1 thing called the Graham determinant. So it's a determinant of this where you take legs n minus 1 of the legs of the process, because it has, this is for n not too big. So this is called the Graham determinant, or sometimes the Grimm determinant. I think Keith Ellis came up with that one. It's Grimm because you get factors of it in the denominator, and if you're near where it's 0, you could get numerical instabilities. So let's just look at a couple examples of these Graham determinants. So first example is the 3-mass triangle. So if you have a one-loop integral, for example, if you're doing something with 4 partons and maybe an off-shell photon or a Z or something, then this process will contain also terms where, or graphs, where you have these, and then this will involve a triangle integral where this leg has q squared not equal to 0 for the Z, and these will also be off-shell. So you'll have these 3-mass triangle integrals, which if you had some massless legs on the outside would look something like, might be labeled something like this. So then the external momentum, maybe I should call it capital K1, is K1 plus K2. K2 is K3 plus K4. And K3 is K5 plus K6. So the gram determinant for this is twice the dot products of the legs sticking out of the triangle. So K1 squared is, it actually comes with a 2 because of that definition. This turns out to be minus something called the Chilean function of S12, S34, S56. And this is also the phase space for the for a decay. Where the vector minus K3 decays into the particles with mass K1 squared and K2 squared. So it only vanishes at threshold. So there are some extra singularities when you reduce down integrals like this that contain this 3-mass triangle, but you kind of know at least where their singularities are. But they still cause some, could cause numerical instabilities, because you could have 1 minus delta 2s to pretty high powers times various of these 3-mass triangles, and then you would have bubble integrals, and there would be numerical cancellations between these. The answer would be relatively smooth near threshold, maybe up to logarithms, but there would be apparent power law cancellation. So this is just something you have to watch out for when you're trying to make these things numerical in the end. And there's similar things that happen with box integrals in other regions of phase space, but I think I won't go through that in any detail. So are there any questions about that? Otherwise, we might start moving on to 2 loops. So in contrast to the 1-loop case, where basically all the integrals have been known forever, the 2-loop amplitudes, the name of the game is really evaluating the integrals. They're known for fewer examples with fewer numbers of legs, and so it's not so much about presenting the integrand in the right way, although sometimes that helps, and it has been used at 2 loops. But you can also generally chunk the Feynman diagrams directly through if you have a good enough machinery for reducing all of the integrals. So the bottleneck is the integrals. So one issue that comes up when you do the reduction is that let's look at a two-loop all massless box. So you have P here and Q here as two separate loop integration variables, and that's P plus Q. And we ask about just ask about the tensors. And if we have a P dot K1, then that's the difference between these two propagators. So that's kind of like a one loop, okay? So that will cancel propagators, and whenever you cancel propagators, you get a simpler integral. So it's always a great idea to do it if you can. And P dot K2 is the same thing. It's related to a difference of these two propagators. But if we are handed P dot K4, so that's, we call that irreducible numerator, an irreducible numerator. You might also worry about 2P dot K3, but that's not independent because it's so that's where we dot this one into this one. And then by symmetry, there's another irreducible numerator on the Q side where we dot, so we have two different irreducible numerators in this case. And so that's something to keep in mind that's different. And now we're going to introduce the integration by parts. And give some examples before, and then we'll apply it to the to a more realistic case next time. But I'll just give a few simple examples first. So integration by parts, which is always called IBP. It dates back to its use in propagator integrals, two-point integrals at multi-loop by Chaturkin and Kachov in 1981. There's also a book by Smirnov on it called Feynman Integral Calculus. And then a big breakthrough was made by Laporta just down the road in Bologna, where he figured out a better way to let the computer solve everything. There's a review by Grozan. And there's a review by, I think it's Abroy Brito, which also goes into differential equations and related things too, which just came out last year. So the basic idea is to enlarge the space of Feynman integrals that are related to each other by and the number of equations as we enlarge the space grows at least as fast as faster generally than the number of unknowns. So we can use all the equations to reduce tensors and related integrals to a set that can't be reduced any further by IVPs, which are called the master integrals. And then we can also take derivatives with respect to parameters of these two-loop integrals, and we can reduce them down to the integrals again. And that gives us differential equations. So that's the general strategy. And now I'll give a quick example or two before finishing today. Any questions about the general idea? So we'll do a one-loop toy first, and then a second toy, and then we'll go on to to a massless box integral. See how that works. So we have an integral we want to do of a propagator with momentum p, a single propagator, and mass m. So the idea is to generalize it by raising this to a power nu, which is a generic integer. Now in this case, we can use the relation that if we have 1 over something to the nu power, we can write it in a slight generalization of the Schwinger parametrization formula we saw earlier as e to the minus t times this, but now we need a t to the nu minus 1. And when you do this integral, you get 1 over a to the nu, but you also get a gamma of nu, and so you need to divide through by that factor. When you plug that in to here, you get a Gaussian integral, and when you do it, you find that I nu has a minus 1 over nu, which is related to Wick rotating the p to minus p, you get a minus 1 to the nu. You get a 1 over gamma nu from this prefactor, and then after you do the Gaussian integral, you get a shift by something proportional to the dimension d. And then by dimensional analysis, you get something like d over 2 minus nu. Okay, so I did this integral directly, but notice that there's going to be a recursive structure to it in nu. And the reason is that the gamma functions obey identities when they're shifted by 1 unit. And also if you shift nu by 1 unit here, you'll just change things by a factor of m squared. So it's easy to see that I of nu has a recursion relation which looks like this. In other words, if I shift nu to nu plus 1, I'm going to get 1 power of m squared in the denominator more. So if I multiply through by m squared, then that will be fixed. And then this gamma nu plus 1 is the same as using the standard formula for the gamma function. I get a factor of nu, and that will also be in the denominator, so I should move it over to the, I could move it over to the other side. And then this one gives me a nu minus d over 2, and there's another minus sign from here. So this equation is is a true equation. Now let's derive it by integration by parts, and then we'll stop for today. So the IBP relation that we want to write down is just that we get 0 if we integrate a total derivative. And we always assume that we're in a dimension such that there's no boundary term, that things are converging out at infinity. And then later we can kind of analytically continue in the dimension to anything we want, continue the relations. So this should be 0, and then when we just carry out the differentiation, we get a d. When p mu hits this, we get a delta mu mu, and that has, for d space-time dimensions, we get to use this identity. And that just comes with the same denominator, nu. But then, when we differentiate this with respect to p, we get a minus nu, and then there's a 2 p mu, and then it gets contracted with this, so we get a p squared, and then we get a p squared minus m squared to the nu plus 1. And now this p squared, we should rewrite it as p squared minus m squared, which will cancel one of these powers and make it look more like this, plus an m squared term, which we can bring out of the integral. So we rewrite the stuff upstairs in terms of the denominators in general. And when you do that, you get that 0 is equal to d minus 2 nu. This extra 2 nu is from this term. And then there's an m squared term where it's been shifted, minus 2 m squared I of nu plus 1. So if you divide by 2 and rearrange the terms, you'll see that's the same as this equation up here. So we have a space now, which is a one-dimensional lattice. And so we have different nu's. And suppose we're handed the integral for nu equals 5 or something. Then we can solve this equation for I nu plus 1 and then rewrite it in terms of I nu minus 1. That is to say, this equation contains a vector that lowers us by 1 unit. So this equation, sometimes written as d over 2 minus nu m squared 1 plus, where 1 refers to propagator number 1, but there is only one propagator in this case. And plus means that it acts on nu and takes nu to nu plus 1. Anyway, it's just a shorthand notation that we'll use later on, or it's often used to keep track of what's going where. But in any case, you want to solve for the raised integral in terms of the lower ones, and you just keep using that recursion relation until you hit this one at 1. And that's called that would be the master integral for this problem. Okay, this is just a toy example, but next time we'll apply it to like that 2-loop massless box integral over here. Any questions?